So for this lesson, we are going to be discussing end behavior, and falls in that series of lessons that go into the module, the section for limits at infinity and asymptotes. But end behavior is talking about what is the graph doing as x gets really big or really, really small. So our learning outcomes here estimate the end behavior of a function as x increases or decreases without bound. That means going to infinity or negative infinity. And recognize an oblique asymptote on the graph of a function. So you should have seen oblique asymptotes before. I'm pretty sure you have, back when you took your Math 126 class, especially when we dealt with rational functions. So let's move on here. This is just showing, and again, I'm not going to go through it all because I feel you can go through if you want to. But if your power is even, it's either going to come from above and go back up, or come from below and go back down. If your power is odd, it'll come from below and then go up, or come from above and then go down. But that's something you would have seen in your Math 126 days. So here it says for each function f, evaluate the limit as x approaches infinity of f of x and as x approaches negative infinity of f of x. So for our first one here, we look for the limit as x approaches infinity of negative 5x cubed, and that's going to be negative 5 times the limit as x approaches infinity of x cubed. That's going to be negative 5 times infinity, or negative infinity. And if we look at the limit as x approaches negative infinity of negative 5x cubed, it's the same process. That's going to be negative 5 times the limit as x approaches negative infinity of x cubed. So that's going to be negative 5 times negative infinity, or positive infinity. Let's go on to B. We want the limit as x approaches infinity of 2x to the fourth. So that's going to be 2 times the limit as x approaches infinity of x to the fourth. And so we know being x to the fourth function is going to go up in both directions. But so looking at this one specifically, it's going to be 2 times infinity, which is infinity. And the limit as x approaches infinity, negative infinity I should say, of 2x to the fourth is going to be 2 times the limit as x approaches negative infinity of x to the fourth. And being a fourth power, it's going to square any negatives. So you end up with 2 times infinity, which is infinity. So for that one, the end behavior is the same. It's going to go up in both ends. Okay, let's look at example 2 now. So let f of x equals negative 3x to the fourth. Find the limit as x approaches infinity of f of x. So we're looking for the limit as x goes to infinity of negative 3x to the fourth. So it's going to be negative 3 times the limit as x approaches infinity of x to the fourth. So that's negative 3 times infinity, which is negative infinity. Okay. Now let's look at horizontal asymptotes. Horizontal asymptotes of rational functions. A horizontal asymptote of a rational function can be determined by looking at the degrees of the numerator and denominator. Case 1, the degree of the numerator is less than the degree of the denominator, so we have a horizontal asymptote of y equals 0. That's because the denominator gets bigger much faster than the numerator, and it overpowers it. The degree of the numerator is the same, or is greater than the degree of the denominator. No horizontal asymptote. As I discussed in the last section, that you're going to have your slant asymptote if it's 1 degree difference. If it's more than 1 degree difference, you have, no one really addresses this, but it'd be like if it's 2 degree difference, you have a quadratic asymptote. If it's 3 degree difference, you have a cubic asymptote, and so on. But you wouldn't have a horizontal asymptote. That's the point. If it's the same numerator denominator, it's going to be the leading coefficient over leading coefficient. So for each of the following functions, determine the limits as x goes to infinity and negative infinity, then use this information to describe the end behavior of the function. So for this first one, they don't give me a lot of space to work over here, but these have the same power. So our limit as x goes to plus or minus infinity of 3x minus 1 over 2x plus 5, that's just going to be 3/2. It's the same on both of them, leading coefficient over leading coefficient. And the next one, it's a bigger degree down below than on top, so our limit as x goes to plus or minus infinity of 3x squared plus 2x over 4x cubed minus 5x plus 7. That's just going to be 1 degree more on top, so it's going to be 0 because the denominator is going to get bigger much faster. In our third case, it's a higher degree on top than bottom. So for this one, we would do a division x plus 2 goes into our 3x squared plus 4x plus 0. And I guess because it was an x plus 2, I could have done synthetic division. I'll just do the long division. So x times what is 3x squared, and that's a 3x. So you have 3x squared plus 6x. And we're subtracting, we get negative 2x plus 0. Then x times what is negative 2, and that's a minus 2. So negative 2x minus 4, and we're subtracting, we get a 4. So what this really is 3x, y equals 3x plus 2 plus 4 over x plus 2. And notice the numerator is 1 degree less than the denominator. It has to be at least 1 degree less. But as x gets big, this becomes nothing. So it's a slant asymptote of y equals 3x plus 2. That's it. Oh, I guess ask the limit as x goes to infinity of 3x plus 2 is going to be infinity. And the limit as x goes to negative infinity of 3x plus 2 equals negative infinity. I see one correction I need to make, and I just it doesn't make a big difference at all to this, but it is that we were working with the this numerator, or the quotient here is a minus between the 2 and the x, not a plus. So I need to go back and change that. So it's a minus 3x minus 2, minus 2, minus 2, and minus 2. But it's the same result. So there you go. Okay, let's go ahead and move on. Evaluate the limit as x approaches positive negative infinity for 3x squared plus 2x minus 1 over 5x squared minus 4x plus 7, and use these limits to determine the end behavior of f of x equals 3x squared. What I want to point out, though, I don't know if it jumps right out at you or not, but it jumps out at me, is that we're dealing with a polynomial or a rational function that it's the same power on top and bottom. So the limit as x goes to positive or negative infinity is just going to be that leading coefficient. So it's 3x squared plus 2x minus 1 over 5x squared minus 4x plus 7. It's just going to be 3 over 5 because they have the same degree. Now, hopefully you remember that from our fun-filled days in Math 126. Or you remember it from what we just talked about a minute ago. Now, what does this mean by end behavior? That end behavior, it's going to be approaching 3/5 in both directions. So other stuff may happen in the middle, but the end behavior, the long-term behavior in both directions is going to be approaching 3/5. a horizontal asymptote 3/5. So that's what we're after. That's what they're asking. Okay. Now we'll talk a little bit about the oblique, or also called slant asymptotes. No, I'm going to take that back. So determine the end behavior for a function involving a radical. So this looks stressful when you first see it, like, oh my gosh, what am I going to do? There are several ways to deal with it, but really what's happening here is we have an f of x equals 3x, and then there's, plus dot dot dot. I know there's a minus 2, but my point is it's 3x is what's happening at first. And then think of it as a square root of 4x squared, and then some other stuff. So if we focus on these two leading terms, that's like saying 3x over 2x, and now they have the same degree. I know that's a 4x squared, but it's under a square root, so it's like saying 3x over 2x. So our limit as x approaches positive or negative infinity, and yeah, we can go negative. They're asking for, yeah, positive negative infinity. Of f of x is going to be that 3 over 2. What we might need to consider, though, is with the negative infinity, is it going to be negative? Because down below, it's a squared under a radical, so that's going to produce a positive. So it might be negative. Hang on a second. When I look at the graph of this in decimals, I do see this. It's approaching two different things. So it's that 3x minus 2. So as we go to the right, it looks like it's going towards 3/2. And the left is negative 3/2. So that does account for the negative infinity. So this 4x squared, that squares out the negative, and then you take the square root, and you get the positive for the principal square root. In the numerator, though, the negative is still present, so we need to keep that in mind. So let me do that. Okay. So that we see as you go to the left, it's going to negative 3/2, and going to the right goes to positive 3/2. So I'm going to call this okay. I'm having a little bit of technical problems today. It's all user error. So plus or minus 3/2. So the limit as x goes to infinity is 3/2. Limit as x goes to negative infinity is negative 3/2. I should probably put an f in there. Okay. There we go. Let's keep going. Let's try another one of these. Very similar process, though. So we have the limit as x goes to infinity of the square root of 3x squared plus 4 over x plus 6. So think of this as the limit as x goes to infinity of the square root of 3x squared plus some stuff. I know it's all under the same radical, but I just want to focus on the leading term here, over x plus some stuff. And it's these leading terms that we're after. So if we consider that square root of 3x squared is like saying the limit as x goes to infinity. Boy, my infinities are getting worse. To be honest, I think the Apple Pencil works better than the Microsoft one. The whole setup. So that's going to be the square root of 3 times x over 6 times x. So we're looking at that being square root of 3 over 6. Oh, that was dumb. I just saw my mistake. Backing up. At the moment, that wasn't a 6x. That's just an x. I don't know why I was seeing 6. So x, so it's a 1 here. And that's a square root of 3. But again, they're just asking as x goes to infinity, so we're good with that one. Okay. Let's go on to another example. And this one didn't print out as per the new thing. We have, my version of it's y equals 4x cubed plus 2x squared minus 4x plus 1 over negative 2x squared plus 2x plus 3. And they want to know what is going to be happening, or our end behavior for this one is really looking more like, well, we have a cubed on top, a squared on bottom, so we're going to have an oblique asymptote. So let's look at this as, do the long division. This is what everyone loves to do. It's actually not bad. It shouldn't prejudice people. We have a 4x cubed plus 2x squared minus 4x plus 1. So negative 2x squared times what is positive 4x cubed, and that's going to be a negative 2x. So it's a 4x cubed minus 4x squared minus 6x, and we subtract here. The 4x cubes go away, as they should, because you designed it. I mean, we both picked this to go away. 2x squared minus 4x squared is 6x squared. Negative 4x minus negative 6x is plus 2x. Then we can bring down the 1. And then negative 2x squared times what is 6x squared? That'd be a minus 3. So it's 6x squared minus 6x plus, no, it'd be a minus 9. And I'm subtracting everything here. We end up with an 8x plus 10. So in reality, I mean, if you want to write this out, it's going to be y equals negative 2x minus 3 plus the 8x plus 10 over the negative 2x squared plus 2x plus 3. And notice it's a degree less than what's down below. It'd be at least a degree less. Could be 2 degrees less. Okay, it could be a constant as a result, or it could be 0, which is a constant. But anyway, back to this. We're talking long-term behavior as x gets really, really big or really, really small. And so this is one of the situations where the degree on top is less than the degree on bottom. So this term, as x gets big, goes to infinity, then this 8x plus 10 over negative 2x squared plus 2x plus 3 is going to 0, because you have 0 over infinity. Or sorry, the denominator, 0, infinity over infinity, but the denominator gets bigger much quicker than the numerator. Okay, so it's just the oblique asymptote y equals negative 2x minus 3. That's what describes it. Okay, let's keep going. So these polynomial ones, we have those nice rules. It's kind of easy to see what's happening, but it gets a little bit different when we deal with what we call the transcendental functions, or the 6 basic trig functions. We have e and so on. So we have other things to consider about the end behavior. So when we get down here to it, if I ever can get to it, a problem like this: find the limits as x goes to negative infinity and x goes to infinity and negative infinity for f of x equals 2 plus 3e to the x over 7 minus 5e to the x. So one thing to consider in doing this is dealing with this e to the x situation. So if we look at the limit as x goes to infinity of 3 e to the x. I guess I'm looking at the wrong problem. It's 2. Look at the next problem. 2 plus 3 e to the x over 7 minus 5 e to the x. So as it goes to infinity, you have basically infinity over infinity. So that's the problem. But if we take this and multiply this by 1 over e to the x, over 1 over e to the x, just like you could evaluate the polynomials or the rational functions as 1 over x to whatever the highest power was, and see what happens. This would give us the limit as x goes to infinity of 2 over e to the x plus 3 e to the x over e to the x over 7 over e to the x minus 5 e to the x over e to the x. And these e to the x's will divide out. We end up with the limit as x goes to infinity of 2 over e to the x plus 3 over 7 over e to the x minus 5. So now as x goes to infinity, you end up with 2 over infinity plus 3 over 7 over infinity minus 5. So negative 3/5. On the other hand, this one's kind of interesting. On the other hand, the limit as x goes to negative infinity of 2 plus 3e to the x over 7 minus 5e to the x. Now, if we did the same thing, we would have ended up with 2 over e to the negative infinity, which would have been 2e to the infinity. So we don't need to do that this time, because if I put in that negative infinity, that's like saying 2 plus 3e to the negative infinity over 7 minus 5e to the negative infinity. So in this case, this becomes 0, and this becomes 0, because it's 3 over e to the infinity. It's 5 over e to the infinity, or negative 5. So our result would be 2/7. Okay, we have one more to do. Find the limits as x goes to infinity and negative infinity for this problem. It's the one I started looking at first. F of x equals 3 e to the x minus 4 over 5 e to the x plus 2. So it's very similar to what we just did. So we have the limit as x goes to infinity of 3e to the x minus 4 over 5e to the x plus 2. We'll multiply this by 1 over e to the x over 1 over e to the x. So we end up with the limit as x goes to infinity of 3e to the x over e to the x. And I'm not drawing this very well, so I'm sorry if I'm confusing people. Minus 4 over e to the x over 5e to the x over e to the x plus 2 over e to the x. So that's 3 minus 4 over e to the x over 5 plus 2 over e to the x. Oh, I'm straight out of the viewable zone. And that's going to give us essentially the limit as x goes to infinity. No, I don't need the limit anymore if I'm going to apply that. It's like saying 3 minus 4 over infinity over 5 plus 2 over infinity. So it's 3 minus 0 over 5 plus 0. So 3/5. Now let's look at the negative part of this, and that's a fun one. It's like, hey, finally the negative, there's less work. So we have the limit. No, I can't write there. Limit as x goes to infinity, or negative infinity. My gosh, struggle with drawing simple things. Of 3e to the x minus 4 over 5e to the x plus 2. And if we apply that negative infinity, we have 3e to the negative infinity minus 4 over 5e to the negative infinity plus 2. So that's the first term, and of each numerator and denominator is going to 0. We end up with negative 4 over 2 or negative 2. Oh, am I out of the space? Yes, I am. That's it. Okay, hope this was as fun for you as it was for me.